Alright, so welcome everyone to this final lab session of this course, which is on GANs. So GANs actually stand for Generative Adversarial Networks. And what we're essentially trying to do over here is not only see how do we build basic models through APIs, but also like try to understand what's actually going on under the hood. It's a very interesting concept. So let's actually welcome everyone back to lab session number 9 of this deep learning course. And this is going to be the final lab session. And this lab session is actually going to be on GANs, which stand for Generative Adversarial Networks. And so it's a very interesting topic, quite amazing ideas and concepts going on under there. And so in this lab session, we'll not only try to see what GANs are, where they are used, but also try to build them, train them, and stuff like that. So before we get any further, let's actually start with this. And let me show you what exactly do I mean by a generative adversarial network. All right. So here's a this is what you'll usually see as a representation of a GAN, right? And so the GAN contains a GAN is actually stands for generative adversarial networks. So the task of GANs is usually to generate something. And so I usually always say that there are three kinds of tasks in machine learning: classification, regression, and finally you have generation as well. Now, generation technically can be put into regression or classification, but the thing is that it has completely different training methods and stuff like that, and so it makes much more sense to do that. But it's only my definition, and so take it with a grain of salt, right? Um, Let me show you what exactly GANs can do. There's this website that uses GANs. And so look at this person. You might say that this person is somewhere in this world because it's so well detailed in every way. Look at the hair, look at the details under the eyes, the earrings, stuff like that. The thing is that this was completely made by a AI model, right? With no input at all, just some random input. And so the model is so well capable of generating anything, something. Over here we're generating images, right? Let's try something else. Look at this person does not exist either. It's completely made by an AI model. Let's look at something else. Look at this. um, it's quite uh, plausible. It's hard to say that it's just fake. And so but if it take a closer look, you will find reasons why this is actually fake. So for example, if you look over here, this ear over here, it's slightly weird. There's some weird things going on over here. And look at um, this part over here, this part of the t-shirt which is generated seems quite weird as well. Let's take a look at something else. Right. Yeah, this looks pretty plausible actually. So it's getting harder and harder to recognize, but yeah, so for example, you see something weird over here with the pixels. So and look at this weird blurriness that you find in this region of the face. So it's not that this is technically uh, uh, so realistic that it's indistinguishable, but and you can see like how this works. Look at this website. This X does not exist. So there's this cat does not exist. So this cat does not exist. It was made by an AI model. And look at the amount of details that you can find in this model. This waifu does not exist. All right. Okay. Anyways, so you get the point. That's about GANs. So how do GANs work? What exactly are GANs? So let's actually go back to our image. So if you guys remember that we actually have seen a generative model as such before, which is like the unit type of model, which can take in an image and return an image, another type of image. So that's also a generation task, right? And so how is and that actually is the very backbone of this model as well. So the generator itself, the part of the model which generates something is which is called the generator. This thing over here. Um, Let me find a good image for you. Okay. Anyways, there's a generator which generates the which takes in an input and generates the final kind of output that we want. And so that essentially is a unit type of model because only those models are capable of, I mean, by architecture design, they are the ones that are capable of generating an image out of some input. But it turned out that in the end, we would, match it using mean square error loss, right? And so the mean square error loss was actually not sufficient to create really sharp quality images. So because, well, by mean square error loss, you would sort of have eyes, for example, and so the eyes are very well structured pixels, right? But if you were to like predict something which is off color, off structure as well, the mean square error might be low. The problem is that it will not be sharp enough to like be good enough to do that. So in 2014, um, Ian Goodfellow, which is now the head machine learning engineer at Apple, I think. Wait, I'm not sure. Yeah, Apple. Came up with this idea while drinking, sitting at a bar. And let's actually pit two neural networks against each other. And the task of these two networks is to sort of improve each other. So, and hence comes the idea of the discriminator, which is the second part of this GAN model, which is also a neural network model. The task of which is to identify whether or not the images that are produced by the generator is a fake image, which is, I mean, is it a ground truth image or is it an image that is produced by the generator? And that would train, and so the generator would sort of get better over time because the optimization is to simply like reduce the is to sort of reduce the accuracy of the discriminator, and the discriminator's task is to be as accurate as possible in determining which is fake and which is fake in the sense which is generated and which is ground truth. So you can see this what exactly is happening. There's some input going on. Generator tries to generate some samples, and then what we do is that we do a sort of a mixing between real images and the generated images, put them in a discriminator and ask the discriminator to sort of predict. And so based on the accuracy of the discriminator, that becomes a discriminator loss based on which the discriminator is trained because you want to make it as accurate as possible. And based on the generator loss, which is basically how good it was at fooling the discriminator, that becomes the generative loss. And the generative loss is not only like how good it was at discriminating, but how also good it performs with respect to the real images. So it's a sort of sum between the normal mean square error loss and the amount by which it was able to fool the discriminator image module. Enough about that. Let's actually start this problem. And so we're going to be using um, we're gonna be defining a lot of things from scratch, but I wanna save some time by not having to write some very basic APIs like the learner module, for example, and the very basic optimization techniques, because they take a lot of time, right? And we are now dealing with quite heavy stuff. So let's actually not deal with that now. Um, and this actually comes. So this implementation is given in first year's code base, but we're gonna be, like discussing what exactly goes on and how we can sort of optimize it further. So we'll learn about what's exactly going on under the hood. Right. Let's actually start with the first thing that we always do, which is untar data, which is get some data. So for this, we're going to be using a very famous uh, GAN task, which is known as hotel room generation, which is basically take some random input and generate uh, images of rooms, bedrooms, and other sorts of rooms. And so there was this very famous data set called Elson bedrooms. And the task is very famously defined as you put in some random noise into the model and expect your model to give you these images like this over here. Now, I should mention that modern GAN tasks don't actually work this way. Like, there's absolutely no particular use of, like putting random noise into your model because, I mean, it has no practical applications as such, right? And so, a more realistic task would be to sort of, color images, for example, D old D5, right? And so now there are techniques in which you can sort of put in black and white images, let's say images of old pictures, uh, uh, or your ancestors' pictures, right? And you would get very, very accurate colored pictures out of them, right? Look at this. Look at these examples over here, for example, right? It's amazing. And so, tasks like this, or super resolution tasks, in which you would put an image of a lower resolution, which is blurry, and then sort of get very high resolution images out of it. And GANs can actually learn stuff like that. So, for example, right, let's look at this example. Now, I don't know if you can see it, but this image on the left is slightly blurry, and oh, yeah, good example. Slightly blurry over here and very high resolution images over here. And so the method to actually like build this kind of model is self-supervised learning. So you take all these images on the right, which are high quality, you manually make them sort of blurry or whatever characteristics you want your model to be able to identify, right? And then the transformed images becomes your input, and the ground actual image becomes your output, ground truth output, and that's essentially a self-supervised learning task. So I guess our model is almost learned now. Let's take a look, right? I'm going to be opening one particular image. Oh, get image files is nothing but a function that would iterate through all the directories within this path and get the images with certain extensions like PNG, JPEG, or whatever is related to uh, what do you call related to images. So all the kinds of formats which are supported. We usually almost always will find PNG or JPEG images, but anyways. Right, so it seems like a very huge file because sort of and so it's taking a lot of time to unzip too, but that's okay, we can wait. Right. So a bedroom would look like this, all right? All right, so we have our images. Now this data set essentially only contains bedroom images. There are no x's and y's, so we need to construct our x's. Over here, we're actually going to be creating random inputs as the input. So our task would be to sort of create a random input uh, containing, which is of the same shape, the tensor shape or size of as the output image, right? And that's how pairs become. So I'm going to be creating a random tensor. I'm going to name this invisible tensor, right? Because I don't want it to do anything as such. There's no task of it, and I'm not going to be storing it inside my data set, right? Because it's a random input, I can sort of generate it on the fly. So it's going to have all the properties of a tensor only because, well, um, because PyTorch model data sets, so for example, X's and Y's, when I'm going to be creating data loaders and putting them into batches, it needs to be a tensor. Like I shouldn't have to worry about, like checking over there the size of the output and then creating something. So I'm going to be creating a sort of a tensor format which will always store the information based on the output, corresponding output, and whenever we need it, we're just going to fill it with random values, right? Right. So tensor base is actually nothing but just PyTorch tensor with a few extra details. You don't need to worry about that, but stuff like like representation. So when you do repro of some tensor, it has a better representation than the PyTorch version. So that's just tensor base. And I'm creating this class called invisible tensor. You know, it has all the properties of a tensor, except it does not return anything unless we request it to. And so uh, I don't need a special initialization because tensor base it's basically the same initialization as a tensor base, but um, right. So I don't need anything. Now all I need whenever I need anything, I'm gonna create a def show over here, which you're gonna see what the purpose is, and basically this is only for beautification purposes. So later on, what I would want to do is like there is only one category over here, but whenever there are like let's say multiple categories, I would want to sort of like want to show different input and output mappings whenever we're visualizing data sets corresponding to different classes. So I'm just showing a method uh, which simply returns the number of categories that there exist, right? So CTX stands for that. Nothing special as such. And there's going to be one function over here called def generate noise, right? And it's going to take a function which is actually going to be uh, uh, right, which is gonna simply take in some right y and corresponding to that is gonna simply uh, what do you call create what do you call random tensors of the same size. I can define my size over here because it doesn't necessarily have to be of the same size as the input, right? Uh, but what I'm going to do now is simply I'm going to be doing a cast operation, right? And torch dot random size, comma invisible, sorry, invisible tensor, right? So let's actually take a look at what cast function is. It's part of fastai.basics. And you see dictionary. Wait. Um, all right, so I'm just analyzing this function. I'm slightly unclear about what it does exactly. But cast would simply, uh, it's sort of an operation, like sort of like a series of transformations that are called. And so I guess, and so what it's gonna do is it's gonna take in, um, it's gonna create torch dot random of the given size, and then it's gonna convert it. It's gonna initialize it as an invisible tensor, and that's what we're gonna get. Right now, right. That's pretty much it. Now what I'm gonna do is, I'm gonna create a function known as show batch, right? Which takes an x, which is an invisible tensor. Now this is only for the purpose of visualization, right? So tens y is going to be a normal tensor as such. How many samples do we want? Number of categories. By default, if there are no, then we wouldn't need to like sort of divide them by category, which in this case is true, right? Max n is equal to 10, all right? Number of columns is equal to none. Figure size, just random stuff. Oh, sorry, standard stuff, right? Finally, I'm going to take quarks, keyword arguments, right? So now what we want to do is that if categories is none, ctxs is equal to get grid uh, min len samples. So whatever samples we create, either that or max of n. So we are always going to have no more than the maximum n. And I'll explain to you what exactly I'm doing over here. I forgot to add n rows, right? N calls equals n calls, fixed size. This just, I mean, someone has written this argument over here. So what we're basically doing is that we're going to be simply creating one grid of m by n. M is rows, n is columns, and they're all going to be images of the same category. Otherwise, uh, what we're going to do is that, what do you call it? So CT. Otherwise, what if this is not true, by the way? Anyways, categories is going to be show batch And this, by the way, Python key function. So some random object, right? It's gonna get object which is actually defined by this typed dispatch over here. Anyways, take a look at what it is. And so what we're gonna do essentially now, we're gonna take an x, y samples, same stuff, right? Number of samples we give, ctxs, ctxs, um, max n equals max n, and then keyword arguments, right? So if you guys remember that we have a sort of a method to return the number of categories whenever we're defining an invisible tensor. So internally show batch is going to go to the show method of x and the y or the y, right? So that's basically what this is what we have, and then simply I'm going to return the ctxs. I mean, categories is, I mean, technically the representation of images. So it's going to return a grid containing pixels and whatnot. Right. Name X is not. Oh, right. Sorry. I'm going to do another type dispatch over here, right? Which is, let's actually take a look at what type dispatch is. So that you know. So this allows you to change the behavior of the object based on the kind of input that it receives. So for example, okay, so this basically means that if I were to go to show batch, the normal show batch that exists, right? So by default, this is the init that you basically have, which is also a dispatch function over here. So now we have basically changed it according to our needs. That's basically type dispatch. Finally, later on, we're going to need a show results as well. So it's going to take an x, which is going to be an invisible tensor. We're going to have a y, which is going to be a tensor image. We're going to have sample outs categories is equal to none, which is basically the object used to represent uh, the samples, and n rows equals none, and calls equals none. And we're not going to be dealing with basically that. All these things, we're going to make internal functions deal with that. Again, if ctxs is none, ctxs is equal to get grid, which is going to be the function which is going to return the grid of pixels, which will basically be our images. We'll see how that looks like in a second, but same stuff. Then samples uh, and max n. I'm gonna have n rows equals n rows, and calls equals n calls. Uh, I want to do there's something that get grid can do as well, right? Which, and I'm going to be adding basically one vertical bar between my x's and y's. So add vert, which is going to be the number of pixels you want to create those separations, and you're going to see that. Oh, I'm sorry. Wait. So the output showing results is not going to be just xy. It's going to be xy and the predicted output as well, right? So I'm going to be adding that one extra place, right? So now what I'm going to do is I'm going to transform this into b.show. So I'm going to go to the show, which is going to simply return the particular representation of that what do you call tensor over here, right? ctxs is equal to c, maybe some keyword arguments. Now the best thing about keyword arguments is that you can pass in keyword arguments that are not part of the init or the method definition, but if there exists any keyword which matches with any of the arguments in the definition of the function or the attribute, it's gonna pick up that. So you can pass in quads many times throughout. I think I might be for B C uh, in zip outs dot item got 0 ct access and range max n. So uh, the reason I added this extra one over here is because I don't want it to iterate any farther than max n, and so this is a wonderful way to do that. I'm simply going to be returning ct access. Now ct access is going to be a list, right? Which is going to contain, and so when we go over here, uh, uh, and so yeah, you're going to be simply be printing or those, displaying each of the objects from this over here. Standard stuff over here: batch size is equal to 128, size equals 64, which is size of the image by default. Okay, so now we need to actually create a sort of a data set as well as data loader. This in FastAI is clubbed together and it's called a data block. And there are methods to actually do everything. So let's actually create a, okay, so first of all, let's actually define what we actually need to do. So we'll create a data block, the task of which is to find where the data is stored, the path, right? It's gonna uh, what type is our x and our y. How should the model retrieve files from a path destination? We're gonna have how do you split the data, because again we need training and testing data set. Any transformations that need to be applied, right? So let's actually create a deep block, which is going to be a data block, right? So blocks is going to be, now FastAI is actually quite smart enough to identify a lot of this stuff just by seeing what exactly is going on. So blocks is basically like what exactly do we have as the input as well as the output. The input is actually a custom block which on which transformations will be applied. So it's going to be a transform block over here and an image block over here. And so whenever you write transform block over here, it means that FastAI will actually try to find methods like show and and uh, we're gonna actually also tell it like how to actually get x. So for example, and the output is just simply an image block, so which means that there are images stored somewhere and we just need to retrieve it using some functions. So get x, so what is actually the function which is used to generate to actually generate the input, which is transformation block, uh, and that's simply generate noise, right? Now the way getx works is that corresponding to each y, the same input is going to be passed into the x function as well, but that's not going to be of any use. So that, which is why this fn is actually not used anywhere in this definition over here, right? But anyways, size you can define. Size, I mean, can vary, doesn't matter really. Anyways, get y is going to be get image files. right? Splitter, how are you going to split a data? I just want it to be an index splitter. I'm not going to pass anything. By default it does an 80-20 split. All right. Item TFMS, so like what exactly transformations do I want to do on my input, right? Uh, so I wanted to resize this into the size, into whatever size is given. So I've created a size over here, which is size is equal to 64. So the inputs and outputs are going to be sort of always be of the same size always, right? And also define method, by what method you want. So resize method dot crop. So there are different methods like I mean um, wait, different methods like interpolation. Uh, the most famous is probably crop. So we'll use crop over here. It's quite easy. Simply cut up the centermost area, which is of the same size as we want, right? Finally, we have batch transformations, that once a batch is formed out of all the images which are of the same size, now what exactly do you want? So a batch is always normalized. If you guys remember, we haven't normalized anything, so we're going to be normalizing the entire batch from stats. So I'm going to be using the ImageNet, what do you call, weights over here because, oh, not ImageNet, sorry. Uh, I'm going to normalize them slightly higher than zeros, nothing zeros, and I'll tell you why. But let me just write it first. So the first channel is going to be 0.5, second channel 0.5, third channel 0.5. So that's going to be for the mean. For the variance, torch.tensor, again 0.5, 0.5, 0.5. The reason we want to normalize it this way is because uh, when you have random inputs, the random inputs itself is going to have zero median as such, right? So statistically, it's going to be much harder for a model to learn. If you do any weight multiplication with sort of and do an average across something which has a mean zero, it usually will be uh, hard to learn as such, right? And so you want to actually shift it slightly higher than than usual. Like images in general are usually values which are higher than zero, of course, because every pixel has a greater than zero value almost always. We're sort of just doing that, nothing else. And then we can now simply close our data block. Now we can simply create a data loaders. Now we haven't defined where to get our data, so FastAI is gonna do that now, like dynamically. So this path is where you want to store, where you're gonna get the data from. This is also where we're gonna store this data loaders, and the batch size is given in there. Right. I'm gonna do a dls.show back. Oh, there is some error. Not exactly sure what. Let's take a look. Did I use len somewhere? Type POSIX path. All right. What exactly is path over here? POSIX path. So let me just sort of remove this for now. Let's see what happens. That's weird. Just a second. Let me run something. So there's path.get items. So path.get items. Sorry. Uh, Wait. So there's data block dot get items. So you take a look at what exactly this is doing. String type none. Alright. Oh, project's path. Object of type project's path has no item none. Alright, it's weird. Well, Oh, I think I missed something over here. Uh, I did get X and then get items as well. So get image files, get items. All right, got it. Uh, Small error on my side. Basically, get items by default. So, for example, data block. By default, if you don't give get items anything, right? So, uh, uh, by default, it's gonna take path as basically the object itself, right? Get y is sort of then applied on top of the item once it's retrieved from whatever you do, right? And so that was basically a mistake that we did. Anyways, let's continue. Now, let's actually go and do x comma y equal to dls dot one batch, right? We can also do dls dot show batch, which is now this data loaders is actually essentially it's gonna go through all the data sets and by default it's gonna take in your data sets now because initially by default you have not given any show method over here and categories is none, so we're simply returning none, which is why it's not printed. But let's say we give it some method and we'll actually do that later on. uh, or you can do it on your own. You can check the documentation how it's done. X's are going to be printed as well. But since they're just random images, they're not going to be of any use. But anyways, these are the inputs that we expect a model to create whenever a random noise would be given, right? All right. Now we need to implement a GAN module, right? So we're going to start with a very basic GAN module. And a GAN is basically a collection of two different models. So first, let's just create a wrapper, which is going to be a class which contains both of these things. And we're going to call this a GAN module. It's going to be a child of nn.module as always. Right? So this is nothing but a wrapper around a generator and critic model in order to create a GAN. So going to be simply def init self is going to be a generator which is going to be none by default, a critic which is also going to be none. So you have the option to create empty models as well, and we're going to be storing a mode. Like how do we later on this model is going to have the ability to switch between generation mode and the critic mode, because if you guys remember, there's one pass of the critic and then there's one pass of the generator, and the both losses are calculated and then they're both trained. So we need to like sort of and they have different methods of calculation of different stuff, so we need to keep that in mind. So that's going to be go into this gen mode. Whenever gen mode is true, it means that generator is going to be it's going to be in the generation mode. The generator is going to be active. So It is going to be doing a self.gen mode is equal to gen mode, and whenever you have things like this, fast actually has a function called store attr, which is going to be storing everything that we need. We need a def forward as well, self, and there are going to be any arguments which I don't care about. I'm just going to do uh, return, or actually, if you're really confused about this, just you know self dot gen mode equals gen mode, and I'm going to simply return self dot generator star rx if self dot gen mode, else self dot critic uh, self dot critic star rx. And finally, there's going to be one function which is going to help us switch between the two. So I'm just going to name it switch. It's going to take self, and is there any particular gen mode that you want? By default, it's going to be none. So we're going to simply put the module in the generator mode if wait generator mode as specified in the gen mode, and in case it's none, simply reverse the generation mode, right? So if it's true, make it false. If it's false, make it true. So I'm simply going to do self dot gen mode is equal to gen mode is equal to uh, not self dot gen mode if gen mode is wait if gen mode is none, I'll just simply do whatever gen mode is giving us. It's going to be true or false. So I can make sure that there's a boolean in the first place, because otherwise it's just going to be make my life harder. Uh, wait. Yep. Okay. Right. So now we have created basically a wrapper for critics and a generator. So let's actually now create a generator and a critic. First, we're going to create a critic. A critic is nothing but a classification model as such. So I'm just going to create a simple convolutional layer which is going to take some images and it's going to give us some output, right? All right. So now I'm going to create def basic critic in size, channels, and features, standard stuff like a normal convolutional network, and extra layers. So by default, I'm going to create a particular number of layers which usually work well, but if you want n number of layers, you can always create them. By default, it's going to be 0, right? You're gonna have norm type. What kind of normalization you want to do? We usually want to do a batch norm, but sometimes you want to do a layer norm as well. Right now we don't care about that. There are quirks. And now, wait, a basic critic for images uh, and channels. times insize times outside insize, because they're square images by default. Right. So I'm just simply going to create layers, which is going to be which is simply going to be a conv layer first of all. Which is going to take the initial layer is going to be n channels, n features, right? For which is k, because input usually, I mean, you can increase it more than two, because it sort of helps in increasing the receptive size, and you can like converge with much less layers. Stride is going to be 2. We're going to be reducing it by 2. Classification task, we don't need anything. Padding, if stride is 2, padding is sort of 1 to like maintain the shape as such. Uh, Norm type is none. The initial layer, we don't do any sort of what do you call it, normalization as such. Quarks. And so, well, after that, after the first layer, your current size is going to be nothing but half of the input size, because you sort of have a what do you call you sort of like done a stride of 2, right? And so I'm gonna be right. So I've basically now taken the size of my height and my width, as well as the number of channels that I have, and so now based on how many number of extra layers I want, right, I can just simply sort of create what do you call extra layers based on that. So by default, we are not any creating any like complex architectural designs. So like between different channels, you don't need to change the number of channels that are there. So number of features can sort of act as like the number of features in subsequent layers as well. So I'm going to do simply a layers plus is equal to uh, conv layer. So it's going to take current features as well as current features as the output. Stride of 3. Uh, Sorry, kernel size of 3, stride equals 1, padding is none, norm type. Now we can define whatever type of norm type we want, right? And then there are keyword arguments, right? So finally, out of all these number of features, now the output is going to be of uh, your current size itself, right? Because or never mind. It's going to be it's going to be of some size basically. And so what we basically want to do is now we want to keep reducing it until we get one particular output, because it's essentially a classification type. So I'm just going to be adding layers as and when we need it, right? So I'm going to create I'm going to be dealing with kernel sizes of 4 now, because I just want to get rid of values very fast. But like it's not that you can use like very large number of kernels, because they've been shown to like give less accuracy anyways. So so while it's greater than 4, and when it's equal to 4, we can just simply run it through a nice convolution. But layers dot append con layer uh, current ftrs, and now current. See, now we're trying to reduce the number of size by 2. So by default, then we actually increase the number of channels. This is actually the norm. uh, Kernel size 4, stride 2, padding 1, right? Norm type equals norm type, and keyword arguments as always, right? And now update your current features, because it's now greater than, I mean, so it's multiplied by 2, right? And your current size is going to be reduced by 2. And we're going to do an integer division because we can't create images, we can't deal with images that are in floating point integers. We're going to keep on checking this condition as is. All right. So let's actually talk about init. I'm creating sort of a object to get my final layer of initialization. By default, I wanted a normal timing initialization. So if you don't know what a timing initialization is, I think you must have covered it in certain book. Read the paper. It's a wonderful initialization method. Has been shown to improve the accuracy of neural network models by a good amount rather than general Gaussian distributions as such. Uh, a few years ago, it was actually not done. PyTorch actually by default gave only Gaussian initialization as the by default, but now I think it's just timing initialization. Just for clarity purposes, I'm actually writing an init dot timing normal. Right. So what I'm doing over here is that if I've sort of mentioned any initialization method within keyword arguments, simply make it that. But if not, simply use this as a default, right? I'm going to do layers plus equals. So I'm going to have a init default and then dot and then dot conf 2d cur features. 1 as the output, 4 is going to be the size, and I can make sure that that won't be the case because the input is going to be less than that amount of size, right? Uh, padding equals 0. Why any padding? 0. And the init itself, right? And then I'm going to need to flatten it as well because, well, I'm going to pass it in the sense that it's going to be a tensor of one single value that's going to come out. So that's that, right? That's a basic critic. Now I'm going to create a at the end of this input. Now I've created an end sequential, but you have the option to like I'm going to create a function that can help you add in as many number of linear layers that you want based on whatever you want. All right. Uh, uh, but that you can simply like all you need to do in that case is just add in another argument which talks about like at the end and anything. But right now we're just dealing with one output number, so we don't need anything. All right. Now here's the thing. Uh, you So corresponding to each image, you're gonna get one number, and then that number will go to a MSE type of loss function. All right, but let's say the input was for 64 comma 3 comma 64 comma 64 64 64 height and width. 3 is the number of channels and 64 is the batch size at the end, right? But the output is going to be 64 comma 1, right? And so you need to sort of match the dimensions in order for loss to actually calculate better. So I'm going to create a function that's going to add those channels at the end, right? So again, it's going to be module, always module. I'm going to do simply dim channels at the end of the output for the loss to work without throwing error or calculating along the wrong direction during casting. So there's simply going to be def init self endims self dot endims equals endims. Why is it not a function? Why is it a class? Only because I can simply like add it after the basic critic model and like sort of create an entire pipeline without having to add in separate transforms. Return x.view. I'm simply adding one the start list x.shape. Then you have one star self dot inputs. Right. So I'm simply adding one at the ends. Uh, in order to get the desired shape, and it's going to be part of the same computational graph, and that is why we use x.view and not create a copy or anything like that, so it's memory efficient as well. All right, let's create a basic generator now. So I'm going to have add delegates again, because so what I'm doing over here by add delegates complet in it is basically I'm telling the function that whatever function I'm gonna do at the end, it can by default it can have the same arguments as in what do you call uh, you're also overloading the same arguments as that exist in the conv initialization, and so when I'm going to be passing my quarks within this conv, it's going to have all those by default values which I didn't even bother to pass over here. Uh, that reminds me, let me also put our delegates over here. Add delegates conv layer.net. So I'm adding all the arguments over there. Right. There's going to be outsize, there's going to be n channels, there's going to be in size, which is by default 100, because remember random input tensor was 100 in size. Then you have n features. So what exactly is the intermediate layer size that you want? Same stuff, n extra layers and then quarks. By default, I'm going to name it 64. And you have n extra layers equals 0 by default. Then you have the keyword arguments, anything apart from the ones from the conv init. That works. So a basic generator from insize to images of size n channels times outsize times outsize. Notice the adaptive behavior. It does not depend on the input size. The architecture dynamically changes with whatever input size you set in this class. Right. So let's actually start. And so initially our current size is going to be, sorry. It's going to be 4 comma n features by 2. And so why is that? Is because, well, um, uh, you basically, well, I mean, it's gonna take uh, basically just a random tensor as the input, 100 shaped random tensor. It doesn't even have to be like images of the same shape as the output tensor. And so from that, we're actually going to be creating uh, shapes of the image shape that is actually required. Now, this current size of 4 is actually used to uh, sort of um, learning about is to sort of make sure that when it is actually passed through a generator. Now, so what I'm going to do is, like, I'm actually going to be transforming it over here. Wait, while current size less than out size, right? Current size times equals to and current features times equals to. And so the end result is that current size is going to be larger than the output size, and it's a multiple of 4. So when it goes to a generator, when it's going to be continuously dividing over here, you're always going to make sure that it's either equal to 4 and then it becomes 1 directly. So one-to-one mapping becomes sort of an easier method to deal with things. So makes life easier for the generator. So layers equals add channels 2, right? Because it's going to be an input of 100 size, and then, I mean, an image is basically of the size like of 3 comma 100 comma 100, 3 comma 64 comma 64 or whatever. So we need to make sure they're compatible. So don't need to worry about dynamically, because like why do that is why I created this class over here, which is add channel, which makes it quite convenient without having to do transformations manually. uh, Now I have a conv layer in size, current features 4 comma 1 transpose equals true. I forget why we did conv 2D transpose. So there's a confunc over here. Let's actually take a look at confunc as well. FastAI layers.py, so we can take a look at that as well. Oh, okay. So get attr nm conf transpose f transpose. All right, got it. So basically, we're so instead of, so whenever transpose is true, we're gonna have like the deconvolution operation basically, which makes sense because we want to simply like you're essentially doing a deconvolution operation instead of doing in the unit architecture. You took in an image which was first downgraded into some number of features, encoded and then decoded back up. But you already have a decoded matrix which is a random input of 100, so you directly do a transpose operation, right? Those cards. So few things need to add channels because we will be adding a 2D shape noise tensor as input, but the uh, conf 2D transpose operation uh, expects a 4D input and simply replaces con 2D operation with a con 2D transpose operation, which is a deconvolution or a decoder operation, which uh, is needed because here the input is a decoded vector of some random features. Oh, I'm not done yet, but wait. Right, so that's that. Now my curve size I can again initialize back to 4 because what I want to do now is that I'm going to be, I mean, uh, 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 basically what I'm going to be doing is I need to add as many stride equals to operations as I need. Basically, as many stride operations as I need in order to what do you call reduce the size to a particular shape which is acceptable by the generator, which will not create problems in the generator. The reason I did this is because the current features we wanted to like convert them into number of features, which is I'm going to keep them constant throughout. But the idea is that the initial number of current features will sort of determine what kind of outputs you're going to get once it comes out of that operation. And so now what I'm going to be doing is I'm again going to be going through the same loop and I'm going to create the same sequence of steps, which is going to create the output which can be taken by the generator quite efficiently. Uh, so while cur size less than out size by 2 because add layer until you get to out size. So whenever it's equal to out size, it's gonna turn false and that's where it's gonna end. Right? So you're gonna have layers dot append. Oh, it's outsize. Right. So I'm going to be layers that append conf layer current FTRS by 2, 3, 1, 1, 3, 1, 1 transpose equals true. And then you have quarks. Right? And then you're simply gonna have current features equal, by equal to current size multiplied equals by 2. Right. Finally, just give me a second. Finally, gonna have the final layers, which is simply gonna be uh, layers plus equals conf layer current FTRS again 3 comma 1 comma 1 transpose equals true. Wait, I'll tell you why. Comma star quarks for something in range and extra layers. So because we're going to be creating extra layers, so we're going to maintain this current features over here. And now once we're done with that, we can create the final layer, which is going to give basically the output of the shape that we want over here. So layers plus equals and dot conf transpose to the current FTRS n channels, right? 4 comma 2 comma 1. And now we have actually also made sure that the input is going to be of the same size as the output size. The ground truth image size, because that's how we've engineered our current sizes and our current features, right? Bias equals false because uh, well by right, right. So anyways, you don't need bias over here because well uh, you wait, why don't you need the bias? Oh, right. Think about it, it doesn't actually make any difference as such because uh, your inputs and your outputs uh, sort of um, you already achieved the kind of shape that we already want. The transpose already contains extra number of items that are added in between. So finally, when you're outputting it, it just such doesn't make sense to do bias. Actually, apart from that, I'm not really sure about what exactly is the reason, but I'll take a look if you want. But sort of the convention I've seen. And then the original paper, I mean, this task usually uses a nn.tanh. Turns out, like with in GANs, turns out nn.tanh works better with vanilla GANs than sigmoid. So I'm going to be using that. And I'm simply going to be returning nn.sequential star layers. Right. done with that. All right, so let's actually initialize some objects. So critic is equal to basic critic 63 comma 3. Wait, should be 64. Generator equals basic generator 64 comma 3 as well. Model, which is a GAN module, is going to take the critic equals critic, generator equals generator, and you have the option to like build them on your own. Let's actually take a real tensor and do I want to do real is equal to torch dot random 2 comma 3 comma 64 comma 64, like the batch size as well. Real prediction MDL real by default generator mode is true. No, wait, by default generator mode is false, right? So it's going to go through the critic mode, and in the critic mode uh, the critic mode is going to take uh, basically the image. It's going to pass in values between 0 and 1, which is going to be corresponding to our accuracies of trues and false, right? So it should ideally be 2 comma 1, where 1 is the corresponding access to number which we're going to convert into booleans, and that's going to it's in critic mode. So expect a tensor of 2 comma 1 in shape, which consists of classification predictions. And so let's actually take a look at the shape of this. So I'm just trying to put words, right? Run this, right? Oh, oh. So this floating point, it shouldn't be floating point. Can't assign module before module.init call. Which function is this again? GAN module. All right. So GAN module. Self dot if generator is not none, self dot generator equals generator. Um, let's actually take a quick Google search. Okay. Yeah, it works. And now let's actually go ahead and let's put it into the generator mode. And now let's actually do fake. So ground, the real prediction always means that you know it uses what do you call the ground truth images as the input, and fake usually means that it's the generated model, right? So let's do a noise actually. So noise equals torch dot random 2,100. So now what we have is a fake is equal to mdl noise fake dot shape. So you're gonna see that it's actually the same as wait. Oh, okay. I forgot to consider the case in which it would be none. So add channels has no uh, attribute backward hooks. So over here also let me do uh, super.init. Oh, okay. View argument size must be tuple of ints with an element of type list at position 3. Right. What? Oh, wait. It's wrong. Oh, got it. So yeah, okay, that's that. Well, so so there is actually some mistake why it's not coming out to be 64,64 in shape. Let's actually try again. Yeah, there is some mistake. I'll try to figure out what. Got it. So my mistake, basically I sort of, in the deconvolution operation, I took a stride equals to 1, which is why the shape was sort of just always constant, so it just increased very slowly, right? So um, essentially, yeah, that's basically it. Sorry about that. That makes sense, right? It's always symmetric. So uh, if in the critic we used 4 comma 2 comma 1, here in the deconvolution operation we're going to use the same. All right. Okay. Done with this, and let's actually create other things like the GAN laws. And so let's actually create a wrapper for that. And this is gonna take the GAN module as the input. What was the name of the GAN module? Yep, GAN module. And so I'm gonna it's a wrapper around the grid laws and the gen laws. So simply my init self gen laws func grid laws func what functions you want to use, right? And so you're gonna have a GAN model as well to check like what exactly will be the laws. So you're gonna have super.init, which is gonna be everything which is inside the GAN module, right? And then you have store attra gen this thing. First is gonna take care of everything. It's gonna do that cell.gen loss func is called the gen loss func cell dot blah 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 blah. All right. I have the generator loss over here, so I'm gonna do a generator self output and target, right? And so evaluate the output with the critic. And so my fake prediction, first of all, is simply going to be self.gan model dot critic output, and then self dot gen loss is equal to self dot gen loss. Simply just a wrapper, right? So whatever function you provide to it's going to take in fake pred output target. So um, there's going to be the fake prediction, which is going to be made by the I mean, whatever is the output of, let's say, the generator, it's gonna pass it through the model, whatever, and the task of it is to simply like create uh, predictions as to which is which. So if I give it target, if I give it fake pred, it's gonna mix them up and it's gonna check which corresponds to which. Similarly for critic, you're gonna have self real prediction and the input as well, right? So create some fake thread with the generator with input, and then compare them to the real thread in the self dot crit loss form. So simply going to do fake is equal to self dot gan model dot generator input. Now, since it's only evaluation mode, I don't need requires grad, so always make sure to uh, replace it by false, because I mean, there's not a task over here. My loss is going to be created by the critic loss itself, because well, uh, wait. Oh, sorry, I created gen loss. Now I'm going to do some critic loss. Uh, Now, generator's output in this case, I mean, over here we put it through the generator, and so that's going to contribute to the training process. Right now we are only concerned with the critic, and so we need to, like replace it with requires grad equals false. Otherwise, it's going to be counted within the process. And so whenever we're going to do it in critic mode, the generator has to be freezed, right? So the way to freeze it is requires grad equals false. So fake pred equals self dot GAN model dot critic fake. So self dot crit loss equals self dot crit loss func real pred and fake pred. Simply gonna choose which is which. Okay, so that being said, let's actually talk about like what exactly do we have over here. Uh, Generator is gonna evaluate how close your output was to the target. So output of the uh, generator itself, right? And so it's gonna take the output, which is and so it's gonna calculate the MSE between the output and the target output of the generator, and fake pred and output. So the how good it was able to fool the generator is given by fake prediction. So we need to basically factor in like how well it was able to. So basically, one minus accuracy of fake predictions. So how good it was able to fool the generator. Basically, that's it. Simply, I'm gonna do a return self dot crit loss. Here I'm gonna do a self dot sorry return self dot gen loss. Right. Uh, so just for the purpose of like uh, make life easy, I'm gonna create a function which is with def set freeze model, which is nothing but takes in a model and requires grad equals false. Simply it just replaces things parameters with requires grad equals or whatever you want. Anyways, for p parameter in m dot parameters, p dot requires grad rg. Yeah, that's all I want. Simple helper function. So now let's actually create a GAN trainer. So I'm gonna take in a callback. So now we're creating the basic training loop for GANs. So it's basically similar to that, except now we need to incorporate when the two are sort of uh, trained and when which one is run at what stage. So run after. So I'm creating a variable over here, and we'll talk about what exactly is going on. Train eval callback. Def init self switch eval equals false, clip equals none, beta equals 0.9. So these are all optimization, what do you call uh, methods. Gen first equals false, show img equals true. These are very standard blocks actually. So switch eval is like, are you doing it in the training loop or are you doing in the testing mode? Clip generators can do sort of, I mean, essentially it's just linear interpolation, right? And so you're creating values from something to something. So you want to restrict it between certain values which are statistically possible. So you would analyze it using the ground truth data, like what exactly is the data between, and just predict between that. Your model has to do much less computation based on that. Beta is actually for the averaging of the loss function, because uh, in generation tasks, loss is really, really sort of you know swiggly and very abrupt, not abrupt, very chaotic. So a loss function, a smoothing of loss function usually works well. Gen first, basically, Gen first is it's a very first task critic. I mean, do you want to evaluate using a critic, or do you want to do it by generator? By default, you want to do it you want to run your critic first, just to check like what exactly is your model doing when it's not trained at all, right? Show image is equal to true is basically just an addition word which basically tells this that like, because GAN training takes a very long time and it's very hard to know what exactly is going on inside the model. So like one epoch on the GPU you'll see will take about an hour and a half, let's say, for example. Uh, and so you want to see like what exactly is the model predicting at each epoch. So show image equal true will give you an output sample at the end of each training epoch. Uh, Store attr. I'm simply gonna do switch eval clip gen first. So I'm gonna switch eval clip gen first beta show image, right? And self dot gen loss equal and self dot crit loss equals averaging smooth loss beta equals beta, and again averaging smooth loss beta equals beta. All right, def set trainable. Uh, Basically, what to do when you're in the training mode, right? Train model, the model which needs to be trained as of now is self dot generator if self dot gen mode else self dot critic. In your loss model, I'm going to define this gen mode over here, but later on, but and through callbacks, by the way. Loss model will then be the opposite of that, because you're going to be training one and the output of that is going to help train the other one, right? Self dot generator if not self dot gen mode else self dot critic, right? Now I'm going to set freeze model train model as true, and the remaining one is going to be set freeze model freeze model sorry loss model false, right? uh, if self dot switch eval, So if you wanted to switch it into evaluation mode, then you're gonna convert the both the uh, models to the evaluation mode. I mean, train model dot train. Uh, you're gonna put the training model in the training loop, and the loss model goes into evaluation mode, which is by default true. Sorry, it's not true. The reason what eval does is basically it will do those things like like the dropout sort of compensations and stuff like that. But you should understand that the reason it's false by default is because even though one model is not being trained, it doesn't mean that it's being evaluated. It's still in the training process because the the something is being fed through that model in order to calculate the loss for the other model. And so if you're going to be changing the properties of the what do you call evaluation mode by default, it's not that. So only at the end you're gonna want it to switch it into switch eval, in which case which is gonna be handled by our basically callbacks basically, right? So I'm gonna create some callbacks over here. Callbacks are nothing but functions just called at certain stages of the training process. So before the fitting starts, I'm always gonna be calling this thing. Its task is to initialize smoothness, create, anyways. So self dot generator and self dot critic equals self dot module. So I'm just creating pointers over here. Now I have self dot gen mode, self dot gen first, I have self dot switch, self dot gen mode, right? Because I mean, in the initial stage, gen first is going to decide what's going to happen, and self dot crit losses, self dot gen losses, initially empty lists, and I'm going to apply the averaging smoothness onto that. Now you have self dot gen loss dot reset, and you have self dot crit loss dot reset, uh, which is given by this average smooth loss function, which is by default it's gonna. I mean, the purpose of reset is that well, in the when you do weighting averages, so for example, if you've read about Adam optimizer or stuff like that, the initial layers have to be normalized by a particular value because um, initially the losses are so small that if you apply like a sort of exponential of the beta on top of that, it will sort of be such a small value that it will sort of be skewed very easily by any sort of weighting average, even though it's 0.98 and you're doing a 98 to 2 sort of operation over there. So in such cases, when you reset, it will take care of that normalization process at the beginning. So it's a good. I mean, I'm sure that it must be sort of as such, but the reason I'm doing this is whenever you do a fit, it should not sort of like create problems if you do two fit operations together, right? So that's about that. And def before validate. So when the training ends and when you before you do a validate, right? You do self dot switch gen mode equals true. So in the validation, you want to check during validation. You want to check the performance of the generation mode of the generator in general, GAN critic loss is not a good indicator of the performance generative tasks, right? So that's basically that. And finally, let's see, you have before batch. I'm creating callbacks as of now, right? And let's see, what exactly do you want to do over here? You simply want to clamp the weights with self.clip. If it's not none, uh, and set the correct input output mappings. If self dot training and self dot clip is not none, for p in self dot, the reason I'm checking self dot training is that if it's false, I cannot alter the weights as such. uh, Usually not deal with clipping as such, but I think there was a small clause in the original paper which talked about, or a few papers which talked about like how clamping of weights of the critic is helpful, because um, because the outputs have to be small enough, uh, have to be sensitive to the true and false bias, for example. And so if you see, we've not added any sigmoid as such. You could have added sigmoid, and then this clip would not have been required as such. But larger the weights, there's this problem of exploding gradients and stuff like that, which is especially true in our case because we have, number one, very huge batch sizes, and so whenever you're running through one epoch, you would want to sort of normalize them as such. So over here, I'm just simply setting the uh, just setting some variables, nothing special as such. And so you see that I'm simply reversing my x's and y's. And now the reason I'm doing that is because uh, uh, when you're in critic, the critic evaluation takes an real prediction as the input, and so the ground truth, the ground truth, but I'm not actually sure myself. Oh, so my input is going to be x comma y, uh, which I mean, the x is a random input which is actually not required by the generator, by the critic as such. So yeah, x has to be y, which is why I'm sort of just reversing them over here. The corresponding y is you see critic output. Right. I don't think it has any use. If it does, we'll probably catch it, but I think that's the reason. So I guess a little bit confusing, but it is the way it is. Right now I'm doing after batch. I just need to record my last loss in the proper list of averaged smoothened losses. So I'm just going to be capturing the last element. That's it. If not, self dot training return, because well, if you're not training it all in the first place, then there is nothing to return as such. If self dot gen mode, self dot gen loss dot accumulate, self dot learn, self dot gen losses dot append, self dot gen loss dot value. So right now what I'm trying to do is that I'm going to iterate across all the batches of within my data, all the elements within the data, and I'm sort of going to pass them through the generator process, and I'm going to accumulate all the results. I'm going to be appending the gen loss over here, and then simply self dot last gen equals self dot learn dot to detach self dot thread. Right. Else self dot crit loss dot accumulate self dot learn and self dot crit losses dot append self dot crit loss dot value def before epoch self. And so what I did over here, what in my after batch was basically, if I'm in generation mode, then I would sort of accumulate my generator losses, and if I'm in critic mode, I would sort of accumulate my crit loss over here, and they are all smooth average smoothing processes, right? And so accumulate is actually given by that person, and it will do that smoothing operations internally. Before epoch, just simply put the critic or the generator back to eval if necessary. So self dot switch self dot generate. Right. And you need this because let's say the training process ends over here. Um, Sorry, before you start your training process in general, like so once you start fitting and you reach to this point, if there's any such, if you've set any such method which talks about like, well, what exactly do you want to do to this evaluation, you can sort of like set your models. Okay. Uh, it's actually redefine our switch because it's not as, because now I mean we're dealing with a separate class in general. So basically, need switch not only the model but the loss function as well. If gen mode is provided in the desired mode, switched. So I'm just going to be switching this, right? So not self dot gen mode if gen mode is none, else gen mode, right? Then you have self dot set trainable. So we defined this set trainable over here, which is well, which talks about like what's the gen mode given over here, and based on that it freezes the model based on evaluation mode. Does all of that. Yeah, that's it. And then self dot model dot switch gen mode and self dot loss func dot switch gen mode. It just should be self dot gen mode. So now what I'm going to do is that I'm going to be creating uh, sort of a callback, which I mean, which is gonna simply do. I mean, you have the option to do n passes of the critic and then one n passes of the m passes of the generator, because it's sort of it may be the case that the model is way too slow. I mean, initially the model is basically tugging, the two models are tugging, and so if you don't give them a chance to learn anything, they're simply just going to be stuck in one place. So I'm going to be creating a switcher which is programmable in the sense that you can tell it how many epochs per pass. So sorry, how many passes you want to do per each of these modules. Um, so there's a callback over here. And I'm simply doing a switch to do sorry, switcher to do n crit iterations of the critic, then n gen iterations of the. So this is actually just for fast AI, that once I actually initialize my GAN trainer, then only I'm going to be initializing this. Definite self and grid. By default it will be 1, and so will be ngen. Simply just store these attributes. I'm going to do a def before train, so self cell dot n c and cell dot ng, which is how many passes already done, this will be 0 and 0. So now you have def after batch. So after one batch, you just simply increment them by one. That's it. Switch the model if necessary. So we're gonna do a if not self dot training return, because you don't need any switching at that point. I mean, yeah. So I mean either increment all of the values when it's in training mode or it's in evaluation mode. So for now we're gonna be using the training mode itself. All right. So if self dot learn dot GAN trainer dot gen mode, if one and iter and in and out equals self dot and gen self dot and c and self dot and g, else self dot and c plus equals 1. uh, Finally, I'm gonna create a target, which is gonna be an iter if this instance an iter int else an iter. So what I'm doing over here is that uh, uh, well, right. So this target is basically used to check whether or not we're actually reached the point where we finished the generation or the critic part of it. And well, if we have done that, we will basically just flip it. That's all. So if target is equal to n out self dot learn dot GAN trainer dot switch self dot nc self dot ng, you don't need them anymore, so 0.0 for the next training cycle. All right. Yeah, that's one callback. We haven't defined the losses, the loss functions as such. So I'm going to create my GAN loss functions. Loss gen, loss crit, weights, gen equals none. So we talked about the generator loss. So we'll create a generator loss over here, right? So there's fake pred, there's output, there's target. There's weights gen because I told you that generator loss consists of two parts and we can have the option to sort of weight them down in whatever way. So one is given by the generator, one is given by the critic, how good it was at fooling the critic, basically, right? And so weight gen, right? Weights gen. I mean, initially, I can. All right. So I'm going to create a tensor of ones over here, which is going to be fake pred dot new ones fake pred dot shape 0. So basically just tensor of ones and how many number of elements, as many as the batch size. I have weights gen is equal to, if none, weights gen. Just do a normal addition, which will be one dot, one dot, right? Finally, I have returned weights gen 0 star loss star loss grid fake pred ones plus weights gen 1 star loss gen output. So about like what exactly is a loss gen uh, or loss anything. So we gen loss and crit loss are actually given over here. So by default, each image is gonna have uh, so just a second. By default, uh, critic should be able to predict each image with with a accuracy of 1. So the ground truth is 1, basically. That's that. Then I have def loss critic, which is simply I have def loss C, which is going to take uh, real pred as well as fake pred. So now I'm going to do a ones is equal to real pred dot new ones real pred dot shape 0. I'm going to do a zeros is equal to fake pred dot new zeros fake pred dot shape 0. I'm going to do a return. What is there? An indentation error. Let's see. No, that's not. Return loss crit real pred comma ones because that's loss critic fake preds zeros divided by 2 just for normalization purposes. Now here's the thing, at each step the critic is not only going to get fake images but like real images as well, so we need to like put them together. And so the critic should by default be able to give predict loss critic values as ones and should be able to uh, uh, predict each image each wait ground truth image with a label of 1. Should predict uh, real images as label 1 and fake images as label 0. So let's recap. So I have fake predictions, I have outputs and my targets. Uh, my generator here we are making the critic find should be able to predict each fake thread as a label 0. Here we are here we are checking how good the generator is at is good is at fooling the critic by checking the accuracy of fake thread being predicted as a 1 basically. Yeah, so 1 minus, so I could do a 1 minus loss critic fake thread 1 comma zeros or simply loss critic fake threads 1. That's that. Oh, I need to return something as well, right? Return loss G loss C. So now I'm going to create functions that take the mean and differences between of predictions. Nothing, just simple functions, right? So def take mean fake pred output target y So right now I'm just passing in loss functions. Yeah, this seems right. So I'm going to do a return fake thread dot name. That's it. And then def actually, yeah, def take def real thread fake thread. So I need this because well to check the statistical distribution, because otherwise the only way other way to do that is to simply just check how good it's doing visually. But if you want to quantify it, I guess statistically checking is a good idea. Real thread dot mean minus fake thread dot mean. All right. Finally, let's actually create the learner, which is going to be the last thing that we're going to be doing now, which is simply, I'm just saying that I'm just overriding this as of now, and I'm simply going to do a GAN learner, right? And now there's a def init self DLs generator critic gen loss func crit loss func switcher equals none, gen first equals false, switch eval is true. I mean, initially you wanna turn it into an evaluation mode to check how good it's doing. Show image equals true, clip is none, CVs is none, metrics is none, and it works. Sorry, clip is none. Right? And so my GAN is going to be simply the GAN module that I built, which has a generator and a critic. Right? My loss func will be GAN loss gen loss func and crit loss func. Uh, and the GAN itself, right? The GAN. If switcher is none, switcher equals fixed GAN switcher, and crit equals 5 and gen equals 1. Now the reason I'm doing this is because well, the generator, the critic is basically like a classification model. It needs some time to train in order to get better. Otherwise, initially it's going to be so bad. It, it's going to learn something, but the next time it does it, the generator is already better. So the critic is always going to be at a disadvantage. So which is why that's done this way. trainer equals GAN trainer clip equals clip switch. Did we define GAN trainer? Yeah, we did. Basically, just a callback. Uh, switch eval equals switch eval. Gen first equals gen first. Show img equal to show img. Callbacks. So whatever callbacks, but at the end you always want a loss metric, right? So basically, uh, gen loss, script loss. So this is actually given by FastAI, so to actually evaluate all the losses. And then finally, you want to do a super init, basic learner stuff like self.model, self.dls, stuff like that. So there's dls gan loss func equals loss func cds metrics equals metrics works. I'm gonna put a class method. Class method is nothing but like a like shape, like tensor.shape. You don't have to call it as a function, even though it's defined as a function. So you can just simply call it as an attribute rather than a function without the curly, without the bracket. Right. Here I'm gonna create def from learners in case you wanna like just give it separate learners for generator and critic. So I'm just giving it some flexibility over here. But I don't need it as of now. Uh, yeah, but anyways, like now I'm giving you the flexibility to like not only create different generators, but like separate generator learners or learner objects. And so just makes lives easier. So you can like train the generator separately, critic separately, and then bring them together if you want to. Switcher equals none. Weights gen equals none. Works. So create a GAN module from already trained slash imported gen slash learner objects. Right. So simply now losses are going to be losses is equal to GAN loss from func gen learn dot loss from and then crit learn dot loss func because we've already defined the loss functions. Weights gen equals weights gen, and now I'm simply going to be returning this init method over here, which is going to be cls uh, uh, dls generators, sorry, you have CLS, sorry, CLS genlearn.dls, genlearn.module, uh, critlearn.module, uh, start losses, gen loss, GAN loss, not gen loss. You're gonna have the losses. You're gonna have a switcher, switcher works. Right. Your now class method def. I'm gonna create a nice this Wasserschein GAN, which is a very famous GAN, and that is actually the thing that we've built actually the very basic structures for that. We'll talk about what Wasserschein GANs basically are. But they're basically the same thing. DLs, generator, critic, switcher equals none. Now the clip by default is given by 0.01, right? Switch eval equals false and quartz. I'm simply going to be create a wgan from data generator and critic. Simply going to do return cls dls generator critic take mean take diff. And so what exactly that's the generator loss function and the critic loss function, which is actually part of the assertion can. If you remember, like I mean, generator loss is basically just taking the mean of something, which basically means that uh, uh, you want to reduce the loss, so you want to bring the loss closer to zero, essentially. So maintaining the statistical distribution is the key point in assertion GANs. Clip equals clip, switch eval equals switch eval, and works. That's that. So let me just do some basic bookkeeping over here, which is GAN learner dot from learners are also like delegates. So we haven't mentioned the delegates. Uh, 2 is equal to GAN learner of init. So they need to have the same init methods. So I'm just basically adding the remaining these stuff. Add the remaining initialization variables as in the standard GAN learner metrics, etc. Uh, So GAN. So I'm gonna apply it on GAN learner dot from learners. So I'm basically just updating GAN learners like that. Similarly for WGANs. Right. There's some error. Oh, it disconnected. Yeah, it executed. Uh, GAN leaner, GAN learner, and GAN learner. Right. And so now, let's actually create some basic like WGAN stuff. So, for example, let me do from fastai.callback.all import star generator equals basic generator 64 and channels equals 3 and extra layers equals 1 critic equals basic critic 64 and channels equals 3 and extra layers equals 1. Why not? I mean, ACT partial. So activation class. This actually goes into the quarks, by the way. So it's simply going to be the partial and then dot leaky value negative slope equals 0.2. So I'm just giving an example of how you can build your own models like this. So that's a critic. Learn is equal to O and then dot leaky O rel with a U capital. Oh no, wait. L and U capital as well. And negative slope as a VE at the end. Right. Learn is equal to GAN learner dot WGAN DL's generator critic of func equals RMS prop. So as quarks show image equals true. That's that. Learn dot some metric metrics. Right. Right. Loss metric object is not callable. Loss matrix, chain loss, grid loss. loss metric. So this should be, oh wait, oh wait. Okay, my mistake. So there's trainer and there's switcher that has to be added to callbacks. Metrics is loss metrics, gen loss, crit loss. Uh, right. So now it shouldn't give the error. Yeah, sorry. So I was trying to call something. So metrics is just like an object. And callbacks are called. So you can call an. I mean, so yeah, I put it in the wrong place. My bad. I'm gonna create two objects called recorders, which is gonna help us, dot train metric equals true. So it's making FastAI tell the learner that keep track of these things as well. So don't keep track of valid. Keep track of what do you call it? The training. Don't keep track of training metrics, not of the valid metrics. So and let's finally just train it anyways. Where dk equals 0.0. And let me actually run it on GPU because I mean let's actually see what's the ETA. It's gonna be huge, huge. Not even kidding. 6 hours per one episode. No, actually, but that's only because I ran it on um, a CPU. But now that I'm done with everything, I can probably just go and run it back on my GPU. Runtime, run all. Download is going to take some time, but let's actually stop over here with that. And so you can actually see a model train at once. Probably won't see any results as such because you need to train for at least 40 epochs. And also because we did a very basic task, which is taking in random inputs, which is not actually a good way to use GANs to its fullest potentials. The best ways are to probably use it for like improvement tasks, like, like black and white to color images, or like old people to young people, or um, stuff like that. Removing noise from images, or like removing blemishes from old images and restoring them to good quality and stuff like that. Anyways, we're done with this lab session as well, and with that we'll finish our lab sessions. And next you're gonna actually have an assignment, which is gonna be to build up sort of a practical model, and you may or may not use anything from this lab sessions. These contain some very good idea about like how to build models as such, um, how to build practical models, how to deal with data, how to like write code in an efficient object-oriented programming manner, which is efficient and flexible, customizable to the very core. And so with that, we're going to be finishing this, and all the best to you guys, and see you guys again sometime in the future. All right.